Yeah, hi everyone. Can you guys hear me? Hello? Yeah. Okay. So, yeah. So, good afternoon, everyone. Uh, this is Arpit, and I am your TA for this course, Introduction to Biostatistics. And today we are at live session 8, which is technically the last one, but we'll also have an extra session on Monday where we'll revise and go over the whole syllabus so that it's helpful for your exams. Yeah. So yeah, as always, here are some important links. The first one is the link to the live session. Then we have the link to the YouTube channel where all the recordings of these live sessions have been updated. And then we have the Google Drive where I have uploaded all the materials for uh, whatever we have discussed in the live sessions. Right. So uh, we'll get started with practice assignment 8. Uh, Before that, does anyone have any questions or doubts that they would like to ask or discuss? Okay, so we'll get started. Uh, the first question is, mhm, in an experiment to compare gelatinous activity among three different cell lines, namely A, B, and C, using gelatin zymography, the following sample variances were obtained. So we are talking about some experiment where we are trying to find what is the uh, activity of a given enzyme. And by using some technique, what we are trying to see is in three different cell lines. Uh, for the sample that we got, these are the sample variances at the number of readings or number of samples that were taken. Right, is for each of these cell lines. So what we are asked is to calculate the pooled variance. So when we talk about pooled variance, generally we are talking about, so S square is basically in this case n1 minus 1 into S1 square plus n2 minus 1 into S2 square plus n3 minus 1 into S3 square whole divided by n minus 3, because we have three cell lines, right? If we have k number of populations or k number of k number of populations or samples, and for each of them for different things, then what we can do is we can continue this. So n minus 3, n3 minus 1 into s3 whole square plus dot 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 till nk minus 1 into sk whole square, right? And the bottom denominator would then be n minus k. Right. So what we know is we know n1, n2, n3, s1 square, s2 square, s3 square. So it comes quite easy. You just write down the values. So n1 minus 1 is 5 minus 1, 4 into s1 square is 6 plus n2 minus 1 is 7 minus 1 is 6 into s2 square is 6 plus n3 minus 1 is 8 into 8 divided by n minus. So this n is basically the summation of all the n's. N1 plus n2 plus n3. So it should be 5 plus 7, 12 plus 9, 21. This 21 minus 3. We have 24 plus 36 plus 24 divided by 18. 124 divided by 18, which is approximately 6.88. So the answer here will be 6.88. Okay. The next question is, in a study, subjects are randomly assigned to one of three groups: control, experimental A, or experimental B. After treatment, the number of subjects showing improvement and the number not showing improvement in each group are recorded. The appropriate statistical test for comparing these counts is A, t-test, B, correlation coefficient, C, chi-square test, or D, analysis of variance. So in this case, what are we doing? We have a study where we have three groups. So let's say control A and B, three groups. After the treatment, number of subjects showing improvement and number not showing improvement is recorded. So basically, we have improved, not improved, and we have the numbers here, okay, for each of these. So what we want to do is we want to compare in between them. So we can do t-test, but like since we have more than two cases, we have to do multiple t-tests. So in that case, it's better to do analysis of variance or a ANOVA. Okay. So in the ANOVA, what we'll have is basically a mu1, mu2, and mu3. All of them are the same. That will be a null hypothesis. And our alternate hypothesis in an ANOVA is that at least one of the mu is different. Right. So we do an ANOVA, then we figure out if the means are the same or not. So at a time, we can check for all these three groups and we can figure out if at least one of them is different than the other. Okay. The next question is, in an experiment, to compare protein expression levels among three different treatments, control drug A and drug B, using Western blot, the following sample variances were obtained. Calculate the pooled variance. Again, we have three cases here. We have three N1s, three N's, and three S squares. So three sample variances and three number of samples. So we'll do the calculation. As we know, N equal to N1 plus N2 plus N3. It will be 5 plus 5 plus 5, 15. Then we have S square will be equal to N1 minus 1 into S1 square into minus 1 into S2 square plus N3 minus 1 into S3 square divided by N minus 3. So N1 is 5, 5 minus 1 is 4, into S square is 4, plus into again is 5. So this is 4 into 6 plus 4 into 8 divided by 15 minus 7. So 15 minus 3 will be 12. So what we can do is instead of multiplying all of this, we can write 4 into 4 plus 6 plus 8 divided by 12, which is 4 into 3. So this will cancel out. We get 3 here. 4 plus 6 is 10 plus 8 is 18 divided by 3. The answer here will be option A, 6. Okay. Does anyone have any questions or doubts? The next question is, in an experiment to compare the protein expression levels among 3 different treatments, control, drug A and drug B, using Western blot, the appropriate statistical test to determine if there are any significant differences in protein expression levels among the 3 groups is dash. So again, here we have a very similar kind of situation which we had in question number 2. We have 3 groups and we are trying to test if there is difference in the protein expression level among these 3 groups. So we'll have control, we'll have drug A, we'll have drug B, and we'll have some expression level data here, right, from multiple samples. So what we want to find is the mean of this, the mean of this, and the mean of this. Are they the same or not? So since we are comparing more than one groups here, and we basically what is don't want to carry out multiple tests, the most appropriate test to do here first would be to do the analysis of variance or ANOVA, because that, as I told before, in that you have the null hypothesis that all 3 are same, and the alternate one is that one is at least different. Right. So once you figure that out, you can continue doing other statistics. The next question is TSS is, so this is in terms of ANOVA. We have TSS, which is the total sum of squares. So the total sum of squares in ANOVA can be divided into 2 parts. One is the SSR, or the sum due to the treatment, and one is the SSE, or basically the sum accounted for by the error. So the answer here will be option B. So question. Okay, no, sir. Okay. Yeah, thank you for responding. Okay. Then we have what is the estimate of common variance, or the MSE in ANOVA. So the mean square error of the MSE, which is the estimate of variance, is given by sum square error divided by the degrees of freedom, which is n minus k. Right. The next question is, if there are B number of blocks and K number of treatments in the population, then how many samples need to be done? Okay. So we are talking about ANOVA now. So let's say we have B number of blocks and we have K number of treatments. Right. So then how many samples we need. So for each of these, we'll need a sample, right? Since we have K blocks and B blocks and K treatments, for first this two will need one sample, for these two will need one sample, and so on. For all of them, we'll need a sample. So the answer will be B into K, which is option C, BK. So B into K is the number of samples we need in total. Next question is, in a study examining the relationship between the concentration of neuraminidase and the response of diabetic wound healing, the following regression equation was derived from the data. So y equal to 980 minus 0.565 into x to see how x and y are related. We are given four options. One is independent. So x and y are independent or not related. B, x and y are negatively correlated. C, they're directly correlated. D, they're exponentially related. Now, if you look at this equation, it's very simple to say that basically both of them are negatively correlated. That is because you have a minus term here accompanying the x. So the coefficient of x is negative, when coefficient of y is positive. So what that means is, as y increases, x will decrease, or as x increases, y will decrease. Right. Actually, as x increases, y will decrease. Yeah, because if we draw the line also, we'll get something like this. This is the relationship. This is 980, and the slope of this line is right. Now the next question is, which of the following experimental scenarios would benefit from using a randomized block design? Right. So a randomized block design is basically where we divide the data into different blocks, and then we try to randomize within the blocks. Right. So this is, so we'll go through the options. So A, population is large. So if the population is large, doesn't mean that this experimental design would give you a better sample, right? If the population is highly heterogeneous, so if the population is heterogeneous, doing a block design uh, might help you, but might not help you also, right? The third is population is reasonably homogeneous. So if the population is homogeneous, then there's no need to do a block design, right? Because everything is almost the same. The fourth is population can be grouped into subpopulations. So this is the correct option. So if you have populations which can be grouped into subpopulations, then it's better to do a randomized block design within these subpopulations. So that, because what you would expect is within the subpopulation, there might be some differences that might be giving you different values. So for example, let's say you are developing drugs, then it's better to treat, basically test it on different subpopulations of people. So basically people from different places, so that you know that the drug works in all of these subpopulations, because there might be some genetic differences which might be leading to differences in metabolism and things like that, right? Next question is, in an analysis of variance, another comparing the mortality of E. coli across four different treatment groups with a total sample size of 78. The computed F statistic is 2.3. In this scenario, what can we infer about the p-value? Right. So we are doing in ANOVA, and we are trying to basically compare the mortality of E. coli across four treatment groups. So our K here is 4. We have 4 treatments, and our total sample size n equal to 78. Right. So Okay. So what we'll have here is basically the p-value will be the probability that our if statistic is greater than the hypothetical for degree of freedom between means and degree of freedom within. Right, for a certain value of these two degrees of freedom. Right. So now our degree of freedom between the groups, since we have four groups, will be k minus 1, which is 4 minus 1, which is 3. Then our degree of freedom in total will be equal to n minus 1, which is 78 minus 1, which is 77. So our degrees of freedom for within will be equal to total minus the degrees of freedom between, which is 77 minus 3, which is 74. Right. So we have degrees of freedom within as 74, degrees of freedom between as 3, and then basically we are asked to find this. We are asked to infer about the p-value, right? So what we'll do is we'll basically look at a table, right? So I'll just reshare my screen. So yeah, so if you guys can see here, mm, so for our numerator, we'll have the degree of freedom between the which is based on number of groups and which is basically 3 for us. So we look at the this column 3, right? Actually, yeah, for 3. And we are looking at alpha value of 0.025, right? So, and then for a second degree of freedom, which is for the denominator, we have df within is equal to 74. So on the third column, we'll check for 74. You can't get 74, but we get 70, 75. Right. So that places us somewhere between, somewhere at around 3.31. Right. So for alpha value of 0.025, 3.31 will be the value. Our value is 2.33. Right. So we'll just look for alpha 0.01, 0.05. Okay. So a number of treatments here is 3, and basically the other one is 75. We have around 60 here. So anyways, the value for 60 is 1.85, right? So what we can say here is that our value is 2.33, which is greater than 1.85, right? Just try to look for a better table, which is See this. Again, here we have 3 and 60. Six. Plus 3.5. We will see this options. Okay. So I forgot to go through the options, but since the options are mentioning 0.5 or 0.05, so what we can do is we'll look at this table for 0.05, the F value, and we have our DF of the numerator is 3, and the DF of our denominator is 74. So we'll go to 75, which is closer, and we'll see that the value here is 2.73. So that's what we'll note from this. The value is 2.73. So at alpha value of 0.05, RF critical is 2.73. Yeah, 2.73. Right. So F statistic, calculated F statistic is 2.33. So what this means is if you basically draw a F distribution, which looks like this peak here is 1. We have our value F statistic, which is 2.33, and our F critical is 2.73. F critical is our F calculated. So our F critical we calculated for an alpha value of 0.05. That means the area here is 0.05, but our F value is somewhere here. So the area that is basically here, or the P value that we'll get here, will be greater than 0.05. Right. So the answer here will be option D, greater than 0.05. Right. Now, most likely it won't go till 0.5 because it's a bit to the right of it. Right. So the safest option here would be to go with option D, greater than 0.05. Does anyone have any questions or doubts? So thanks for the table. I didn't see that. Question 11. Which of the following assumptions is required for ANOVA? Option A, samples are drawn from populations with equal variances. B, populations are non-random. C, the dependent variable is categorical. Or D, the samples are random. So the correct answer here will be option A, because in ANOVA, we are assuming that whatever samples we are getting from whatever populations, all of them have equal variances, and that variance is equal to sigma square. Okay, so that's the basic assumption for ANOVA. We also assume that what populations are randomly distributed, and basically the dependent variable is not categorical and can be numerical also, and samples are independent of each other. So the samples that we are drawing are independent of each other. Right? So all these three are false. Okay. Yes, sir. Next question is, in ANOVA, the F statistic is computed as, so in ANOVA, if you look back, the F statistic is computed as MST by MSE, which is mean square total divided by mean square of error. So the answer will be option B. So this is basically the F statistic. And based on this value and the value that we get from a table, we decide whether the test that we have done is significant or not, whether the results that we are getting are significant or not. Right. Next question is, which test would be most appropriate to check if the observed frequency of genotypes fits the expected Mendelian ratio? So in this case, what you have is basically you have a observed frequency or count kind of data, and you want to see, so basically frequency data, generally frequency or count kind of data if you have, and we are to see if it fits some expected ratio or distribution. Then what we need to do is we need to do a chi-square test, because that's what a chi-square test looks for. Right. Next question is, a paired t-test is used when A, comparing means of two independent groups, B, comparing means of the same group before and after treatment, C, comparing more than two group means, and D, comparing frequencies in a continuous table. We have covered this in great detail in the past. Can anyone answer this question? You can just type in your answers in the chat box also. Yes. So the answer is option B. So comparing the mean. So basically, when we are using a paired t-test is when we have a population and that undergoes a treatment. And basically, we take samples from here and samples from here. So these are not exactly independent samples, but we want to figure out if there is a difference due to the treatment in the samples. So in that case, what we do is we basically do a paired t-test, right? The next question is, in simple linear regression, the coefficient of determination R square represents A, the slope of the regression line, B, the proportional variance of Y explained by X, C, the intercept of the regression line, or D, the error variance. They'll give you the formula. R square is given as 1 minus this is R by this is T. So this is sum of squares of the residuals. This is sum of squares total. Right. So in this case, what do you think is the answer? So what does R square represent? Is it the slope? Is it the proportion of variance? Is it the intercept, or is it the error variance? So this residuals is also called sum of square of errors, also called as SE. What do you think this coefficient of determination, this R square, represents? Okay. So someone says option C. Are there any other answers? Okay. We have option C and option A. Okay. So the answer is actually not option C or not option A. So what we have here is basically R square is 1 minus sum square of errors by sum square of total. Right. So what this gives us is this total minus error by total. So sum square, so when you basically have some x and some y, and you fit a line which basically predicts your y bar, right? So these are predictions. So these are predictions. These are your data. This is again your data, right? So in this case, the sum square total is basically the total deviation of, so if you draw basically if you have data like this, and let's say you fit a line like this, right? So the error of all the points from your line is basically the total sums of squares. So that is the total uh, actually that's not the total, that's the sum square of errors or sum squares of residuals, right? So basically, let's say you have data of X and Y, then you basically fit some line to it. So you have an equation which is Y prime is equal to beta X plus alpha, right? Some equation like that. Then what you have is for each of these values of X, you can predict some values of Y. And some square of error will basically be the actual value of Y minus what you have predicted, the square of that and the sum of that. So that is basically this. So this line is what you have predicted. These differences from each point in terms of Y and the square of that, that is the error that your line is showing. So when we are trying to build a line using ordinary least square method, what we are trying to do is we are trying to minimize this, right? So this sum square of error is what we are trying to minimize. So the other thing, so the sum square of error, then the other thing is the total sums of square, which is basically Y minus Y mean, right? So that is basically how far away your value is. So all the points that you have, how far away are they from the mean, from the central point? So that is the total variance of the data in a way, right? So this is sum square total. This is what is basically if you divide it by n, you get an unbiased estimator of the uh, sample variance, right? So this is your total sums of squares. Now your whatever you are left here with after you do this subtraction is basically you are trying to get a term which this term basically looks like summation of y hat minus y bar whole square. Right. So this is like what is the deviation from the mean that is being predicted by your line. Like, do you get that? So basically what we are, so this is also a variance term. So we have a variance, which is the total variance. So this is the total variance of data in y-axis. Right. This is basically the variance that can be attributed to error in our predictions. So we are making this line as a prediction. Whatever errors we are getting after that, so that is basically the variance that can be attributed to the error, right? And since this thing, this SSE, and so this sum square total is equal to sum square error plus sum square of actually forgot what this is called, but let's say this is called sum square of mean or something for now, temporarily. I'll check it out. So what we have is basically, so this is basically this is the total variance in our data. This is the variance that can be attributed to error. And what we are left it with is the variance that can be attributed to our predictions. So this term basically tells you how much of our variance is due to our prediction being away from the mean of the data, right? So this is basically the proportion of variance in y that is explained by our x, or that is explained by this equation that we have of x and y, right? So the r square is something that we'll have for a given line that we predict. So for that line, what is the what is this? What is the proportion of variance that the line is explaining in terms of x and y? So as I said before, what we are trying to do is we are trying to minimize the sum square of error. So if you are trying, so the sum square total will always remain the same. And the sum square error is what we are trying to minimize. So if you minimize this, this will keep on increasing. So what we see is basically that if we have what do you say? So since our this term directly relates with our R square value, right? In the numerator, we have this SST now, right? So this R square, so as this increases, our R square increases. So as more and more proportion of the variance in the data can be explained by our line, so the better our prediction is becoming, and therefore the R square of the line is increasing. So, okay, just to feel like it's getting confusing. Does anyone have any problems understanding this? Then just so let's say we have points like this and we fit a line through them, right? So we have x, we have y. Now for y, right? So we have points here, right? So for y, the best point estimate of y would be the mean of y. Let's say this is y bar. That is the best point estimate of y. So if you want to say that the value of y is something, you'll probably use the mean as a way to describe it, right? So now what we have done here is we have a predicted y, which is the line. So this is basically alpha plus beta into x, right? This is the line that we have drawn. So the total variance, so sum square total is basically y minus y bar whole square sum of it. Right. So this basically represents what is the variance of this y from the mean value. Right. Then we have SS error or residual, which is basically we have this line that we have predicted. So for all of these y values, how different are they from that line? So that is basically y minus summation. Right. So this is our predicted y, which we get from the equation. Y is the actual dots. So each of these dots will be yi. Right. So our actual dots are yi. So our y represents basically actual values. So this is yi. Right. Then we have SS regression. It's actually called SS regression. So this is basically yi hat minus y bar. So what this tells us is basically our predictions or are the line that we have built, the line that we have predicted, how much is the line deviating from the mean, right? So yeah, so how much is the line deviating from the mean? So this basically, so if we have only y, we can describe y as the mean of y. But if we have x and y, and we want to describe y in terms of x, so what we'll do is basically, we'll try to write an equation like this, alpha plus beta x, or something like that. So we get a y hat, right? Now, basically, what we are trying to see in this sum square is basically how different is our prediction from the mean. Another way of looking at it is basically how much variance can be explained by the values we are predicting. Right. So if you imagine we put a line like this, right? So in that case, our y minus this thing, y minus y hat, this sum square of error will probably be higher. And also what will be higher is this minus this. So our, the sum square of error will be higher and this thing will be lower. Right, the sum square of a regression, because the sum square of error will be higher. So basically, what the relationship we have here is SS total is equal to SS regression plus SS error. Right. So if this increases, this decreases. If this increases, this decreases. That's the essence of it. And since our R square is directly proportional to SS regression, so or actually our R square is actually given as SS regression by SS total. So this is basically the proportion of variance that is explained by our regression line out of the total variance that is there in the data. Right. Is that clear? Does anyone have any questions or difficulty? Okay. So the next question is, which of the following is not an assumption of chi-square test? So A, data frequency or counts. I have told you before, this is an assumption of chi-square test. When we are looking at basically differences between observed and expected frequencies or observed and expected counts, we look at basically chi-square test. The second one is categories are mutually exclusive. Right. So actually that is also true. So if you are looking at a chi-square test and you have different categories. So for example, you might have treatment A, treatment B, treatment C, and we are trying to see if they are for example, we have a drug, we have treatment A, treatment B, drug A, drug B, and we want to see if basically number of patients healed, number of patients not healed. Right. So this is some number, this is some number, and so on and so forth. Right. So these needs to be mutually exclusive. So once you are there in one category, you can't be there in the other. Right. Otherwise, our assumptions are not valid. The third is expected frequencies in each cell should be at least 5. Actually, that is also a assumption of chi-square test. The fourth one is population standard deviation is known. This is not an assumption of history, so this is false. Right. Question 17. If the calculated F statistic in ANOVA is much greater than 1, this suggests that so F statistic is supposed to be ideally 1, but if it's very far from 1, so if statistic is that is the incorrect thing. Very, very greater than 1. Then what we basically have is we have a distribution. Here. So our thing is somewhere towards the end, right? Statistic is somewhere towards the end. So group means are likely equal. This will be false because we are at the going towards the edge of the distribution. Group means differ significantly. This might be true. Null hypothesis is accepted. This is false because if we are at the end, null hypothesis has to be rejected. The variance within groups is large. This is also false. The variance between groups might be large, and that's why the statistic is very high. So the answer here will be option B. Group means differ significantly. Right. Does anyone have any questions? Next question is, 3 fertilizers ABC I tested for their effect on plant height. The heights in centimeter are recorded as follows. Fertilizer A, so they had the 3 heights, B and C, the heights are given. The overall mean height is 11, right? What is the between group sum of squares? So what we are given is we have C, 3 different fertilizers. For each of them, we are given plant height 10, 12, 11. In 13. Overall mean height is 11. So we can given that x bar, total x bar is 11. Right. So we have NA is equal to B is equal to C is equal to 3. Right. And since we have 3 treatments, our K is equal to 3. So what we'll do is we'll first calculate the sums of this. This is B, 3, 9, 10, 12. Then we have xi bar, which is basically the mean of each of these fertilizers or if treatments, right? So this will be 33 by 3, which is 11, 42 by 3, which is 14, 24 by 3, which is 8. Right. Now we know that what we are asked to calculate is between group sum of squares. So SSR or between group sum of squares is nothing but N into x bar minus x bar. Full step. Yeah, full step. So this is the formula. So here I is for different treatments or different groups. So between group sum of squares we want to know. So Ni is basically number of samples in the group. Xi bar is basically the mean of the group. X bar is the overall mean. So what we'll do is we'll these things and we'll calculate Ni is 3. So Xi bar for group A is 11 minus the overall mean is 11 plus 3 again into 14 minus 11 whole square plus 3 into 8 minus 11 whole square. This is 3 into 0 plus 3 into 14 minus 11, 3 square plus 3 into 7, 3 square. This is 0 plus 3 square 9, 3, 27 plus 27 equal to 54. The answer here is option C, 54. Okay. Next question is using the same data from question 18. The within group sum of squares is found to be 6. So the SSW sum of squares is 6. Total sample size n is equal to 9. What is the mean square between groups? The mean square between groups is nothing but the sum of square between groups divided by the degrees of freedom between groups. Right. So degrees of freedom between groups will be K minus 1, which is in our case 3 treatments ABC 3 minus 1, which is 2. And our SSR is actually not given in this question. It's actually what we calculated here, which is 54. Right. So our MSB, or mean square between groups, is SSR 54 divided by degrees of freedom 2, which is 27. Answer here is option B, 27. Right. Next question is, if a t-test produces a p-value greater than 0.05, which of the following is the correct interpretation at 5% significance level? Option A. So what we have said is our p-value is greater than 0.05 and our alpha is 0.05. So our significance level is again 0.05. So since our p-value is greater than this, that means in our test, so the p-value is basically the area. Right. Our area is, sorry, our area is bigger. That means if this is 0.05, the p-value that we get will be somewhere here, because then only this area will be bigger, right? So that means we should not be rejecting our null hypothesis. First is reject the null hypothesis, this is false. Fail to reject null hypothesis, this is true. Accept alternate hypothesis, false. Text is inconsistent. The answer is option B, fail to reject the null hypothesis. Right. Okay. So this is it for this week. And does anyone have any questions or doubts? Okay, I'll be here for another 20-25 minutes. If anyone has any doubts or questions, feel free to ask. Yeah, let this be here. Yeah, I'll just mark my camera for some time. For internet issues. Yeah. Uh, yeah. So one tail and two tail test of hypothesis. So we have basically distribution like this. So when we are talking about, for example, test of hypothesis, we generally talk about a standard normal distribution or a T distribution, both of which look very similar to this. And basically we have 0 here and generally, and what we have is basically this distribution going from here to here. So this is the distribution, and we are doing a it's not exactly 0, the 0 or mu or some value, right? So when we are doing a test of hypothesis, what we are doing is in the null hypothesis, we have some statement like mu1 equal to mu naught or mu1 equal to mu2 or something like that, something related to the means of one population or two population, right? Is it equal to a constant value or are both of them equal or not? Something like that we have, right? So in that case, what we are uh, trying to do is we are trying to do a hypothesis test to see if this hypothesis holds true, or we should instead follow the alternative hypothesis, which is mu1 is not equal to mu naught or mu1 is not equal to mu2. Right. So this is in case of two-tailed test. So in two-tailed test, we have these kinds of alternative hypothesis where we are basically implying that mu1 is not equal to mu0 or mu1 is not equal to mu2. And in a two-tailed test, our test can be failed, or basically our null hypothesis can be rejected if our value goes beyond certain critical points, which are called alpha values, right? So this is basically, let's say we are doing a t-test, this is t alpha, t minus t alpha, right? So if our values go beyond this or go beyond this, we basically reject our null hypothesis and we say that our alternate hypothesis is true and there is a difference between the means, or difference, or the value of the mean is not equal to the constant value that we are talking about, right? So this is for two-tailed test. However, if we are doing a one-tailed test, our alternate hypothesis is more stricter. So what we are saying is mu1 is greater than mu0, or mu1 is less than mu0. Right. So in this case, what we do is basically, so in a two-tailed test, this is actually alpha by 2, and the area here is alpha by 2. The area here is alpha by 2. But our level of significance is alpha. So the area here and here is alpha by 2, which is divided equally. But when we are doing a one-tailed test, we again have similar distribution. But now, for this case, we'll just check the upper limit, right? So here we'll have 3 alpha, and this area here will be alpha full, and there will be no lower bound here. And if we are checking for this condition, we'll have a test like this, where we have T alpha here, and this area is instead alpha. Right. So now if our value in this case goes beyond this, we reject our null hypothesis. And even here, if the value goes beyond this, we reject our null hypothesis. Right. So the more clear differences is that our alternate hypothesis is different when we have a one-tail or a two-tail test of hypothesis. Right. For one-tail test of hypothesis, we have a stronger not a stronger statement, but basically a directional statement where we have basically the mean is greater than some value or the mean is lower than some value. And on the other hand, when we are talking about a two-tailed test, we are just saying that the mean is different from the mean value, right? So mu is not equal to mu0, or mu is not equal, mu1 is not equal to mu2, right? So that's the main point of difference. The other thing is that in a two-tailed test, we are basically having two boundaries here on the left, one on the left, one on the right, and basically alpha by 2 on both sides we have, right? So the area on under left hand side is alpha by 2, the area under right hand side is alpha by 2. But in the case of one-tailed test, we have only one area and only one limit that we need to cross because our test is directional, and we have basically the value alpha there. Like the whole area is on that side, concentrated on that side. Okay. Is that clear? Does that explain? Yeah, okay. Thanks. Are there any other questions? Extra practice questions. Okay. So as I said, on Monday, we'll have one more uh, extra class, where we'll discuss some extra questions that will be covering the whole syllabus. I'll also, so today I don't have any questions, but I'll try and upload a few of a few more questions in some slides also by Monday. So like we'll just discuss a few questions on Monday, and in the same PPT, I'll have more questions which you guys can solve and basically practice. Right? And for them, I'll just highlight the answers somewhere. Or in case you have any doubts or issues, you can basically contact me or ask on the forum. Right. Does anyone have any questions? I'll be around for 10-15 more minutes in case anyone else joins or anyone has any doubts. And yeah, by our next class, I'll have some extra questions for you guys also, which I'll supply along with the answers. I'll upload that also. Okay, since there are no more questions and I don't think anyone has joined in the last 20 minutes, so we'll stop the class here and we'll continue on Monday. I think Monday we'll have the last session. I'll try and get more questions. So I'll make a set of 40 or 50 questions that you can go through. Right. And we'll discuss some of them that as many as we can and any doubts that you guys have on the class. So thanks for attending. I'll see you again, guys, on Monday. And yeah, that's it. Bye.